Imagine standing at the edge of time itself, looking back over 13 billion years into a universe so dark and empty that not a single star had yet been born. Then, in the blink of a cosmic eye, everything changed. What force could have shattered that ancient darkness, flooding the universe with light and transforming it into the vibrant cosmos we know today? The answer lies in one of the greatest mysteries of modern astronomy, re-ionization. This wasn't just a flicker in the night, it was the dawn of light itself, a revolution that shaped the very fabric of reality. From the first fiery stars to the violent energy of quasars, the story of how our universe woke up is written in the fading glow of those primordial events. And thanks to cutting-edge telescopes, we're finally piecing together that epic puzzle. Stay with us as we unravel the secrets of this cosmic rebirth, because without it, the universe you see tonight would still be lost in shadow. Now, let's step back into the cosmic dark ages, a time when the universe was nothing like the glittering expanse we know today. Picture a vast, endless void, colder and blacker than anything you could imagine. No stars, no galaxies, just a thick, soupy fog of hydrogen gas, so dense that light couldn't pierce through it. This was the universe's awkward teenage phase, a murky silence between the explosive birth of the cosmos and the brilliant dawn of light. After the Big Bang, the universe was a seething cauldron of energy, too hot for atoms to even form. But as it expanded and cooled, protons and electrons finally slowed down enough to snap together like magnets, creating the very first atom's hydrogen, mostly with a sprinkle of helium. You'd think that with atoms in place, light would have its chance to shine, right? Not so fast. These hydrogen atoms were like tiny light traps, greedily snatching up any photons that came their way. The universe was filled with this neutral hydrogen gas and light. It was stuck in traffic, unable to travel freely. This cosmic fog wasn't just a barrier, it was the stage being set for something extraordinary. All that hydrogen floating in the darkness was the raw fuel for the universe's first stars. But until those stars ignited, space remained pitch black. No twinkling lights, no glowing galaxies. It's almost eerie to think about, a universe where if you could somehow stand in it, you'd see absolutely nothing. No horizon, no landmarks, just an infinite starless night. Yet, even in this darkness, forces were at work. Tiny ripples in the fabric of space, leftovers from the Big Bang, were pulling matter together. Gravity, the silent architect, was gathering hydrogen into denser and denser clumps. And in those clumps, pressure mounted, temperatures soared, and the first seeds of stars began to form. The dark ages weren't just an empty wait. They were the calm before a storm of creation, a slow build-up to the moment when everything would change. Think of it like a massive theater before the show starts. The seats are empty, the stage is dark, but behind the curtain, actors are preparing, sets are being arranged. The universe was doing the same thing. All that hydrogen was the set dressing, and the first stars. They were about to step into the spotlight, and when they did, they didn't just flicker on. They exploded into existence with such ferocity that their ultraviolet radiation began tearing apart the very hydrogen atoms that had kept the universe dark. That's the moment re-ionization began, the cosmic fog lifting photon by photon. But we'll get to that revolution soon. For now, just remember, the dark ages weren't empty. They were the universe holding its breath, waiting to exhale light. Now, imagine the universe taking its first bold step out of darkness. After billions of years of silence, something extraordinary finally happened. The first stars flickered to life. These weren't just any stars, they were the cosmic pioneers known to astronomers as population 3 stars, and they were unlike anything that exists today. Picture a star so massive it makes our sun look like a speck of dust. These ancient giants were hundreds, even thousands of times more massive than the sun, burning ferociously hot and bright. But with great power came great sacrifice. Their lifespans were shockingly short. While a star like our Sun can shine steadily for billions of years, these early titans lived fast and died young, exploding in spectacular supernova after just a few million years. What made them truly revolutionary, though, was the light they unleashed. Their ultraviolet radiation was so intense that it acted like a cosmic blowtorch, blasting apart the hydrogen atoms around them. Remember how those hydrogen atoms had been trapping light, keeping the universe dark? These stars didn't just shine, they fought back, stripping electrons from hydrogen in a process we call ionization. Think of it like this: imagine a frozen lake on a winter morning. The ice is thick, trapping everything beneath in darkness, but then the sun rises and its heat starts melting the ice one patch at a time. Those first stars were the sunrise for the universe, breaking apart the cosmic ice that had kept everything hidden. But here's where things get even more fascinating. Because these stars were so massive, their deaths were just as transformative as their births. When they exploded, they scattered heavy elements, carbon, oxygen, iron into the void, seeding the universe with the building blocks for future stars, planets, and even life itself. So while their lives were brief, their impact was eternal. They didn't just bring light to the universe, they set the stage for everything that would come after. And as we peer deeper into space with telescopes like the James Webb, we're catching glimpses of their legacy, unraveling the story of how the first sparks of light began to re-ionize the cosmos. Next, we'll meet the other titans that joined this cosmic light show, quasars, the powerhouses lurking at the hearts of young galaxies, and how their incredible energy helped finish what these first stars started. Now, while those first stars were lighting the cosmic stage, another player was waiting in the wings, one so powerful it could outshine entire galaxies. Enter quasars, the universe's ultimate powerhouses. At their cores lurked supermassive black holes, millions or even billions of times heavier than our Sun. But these weren't silent voids, they were cosmic engines, feasting on gas and dust with such ferocity that they lit up the early universe like beacons. When a supermassive black hole feeds, it doesn't just swallow matter quietly. Instead, it creates a swirling disk of superheated material called an accretion disk. Temperatures here can reach millions of degrees, emitting blistering radiation across the spectrum, from X-rays to ultraviolet light. Some of that energy doesn't just radiate outward, it gets funneled into jets shooting out at nearly the speed of light, stretching hundreds of thousands of light years into space. To grasp the sheer scale of their power, consider this: a single quasar can outshine 1,000 Milky Ways combined. If you placed one where our Sun is, its light would sterilize Earth in seconds. And yet, these monsters weren't just destructive, they were essential. Their ultraviolet radiation was so intense that it could ionize hydrogen across vast cosmic distances, far beyond what even population 3 stars could achieve. Think of re-ionization as a relay race. The first stars passed the baton by ionizing their immediate surroundings, but quasars took it further, clearing huge bubbles of ionized gas around them. Over time, these bubbles overlapped like patches of melting ice merging on a frozen lake. And because quasars were often found in the hearts of young galaxies, their impact was amplified. Galaxies themselves became factories of ionizing light, with quasars as their turbocharged engines. What's truly mind-bending is how long these cosmic powerhouses have been at work. The light we see from quasars today left them over 12 billion years ago, meaning we're witnessing their role in re-ionization as it happened. Telescopes like the James Webb are now spotting even earlier quasars, pushing back the timeline of when these titans first ignited. So while the first stars lit the match, quasars turned it into a wildfire, one that eventually burned away the cosmic fog and let light travel freely. Next, we'll see how entire galaxies joined this light show, weaving their own threads into the story of re-ionization. Now, as the cosmic drama unfolds, another key player steps into the spotlight: the galaxies themselves. Picture these early galaxies not as the majestic spirals we see today, but as chaotic, star-forming powerhouses blazing with youth and energy. Packed with countless young, hot stars, they became relentless factories of ultraviolet light, pumping out enough radiation to strip electrons from hydrogen atoms on an unprecedented scale. What made these galaxies so effective at re-ionization? It wasn't just the sheer number of stars, it was their teamwork. While individual stars or quasars could ionize pockets of gas, galaxies acted like cosmic megaphones, amplifying the effect. Thousands or even millions of stars, all emitting ionizing radiation at once, created vast zones where hydrogen couldn't stay neutral. Over time, these zones grew, merging with bubbles carved out by quasars until the entire universe began to glow with free-flowing light. Here's where things get even more fascinating. These early galaxies weren't evenly spread out, they clustered together, drawn by gravity into cosmic cities. Where galaxies crowded close, their collective UV radiation worked like a team of cleaners, scrubbing away the fog of neutral hydrogen faster than isolated stars or quasars could. This patchwork process explains why re-ionization wasn't instant. It happened in waves, with some regions clearing earlier than others. But how do we know all this? Enter the James Webb Space Telescope, our time machine to the early universe. Webb's infrared eyes are perfectly tuned to spot these ancient galaxies, whose light has been stretched into longer wavelengths by the expansion of the universe. Recent observations have revealed galaxies far smaller and fainter than we expected, yet shockingly abundant. Some of these galaxies are so young, they're still in the throes of their first explosive bursts of star formation. One of Webb's most jaw-dropping discoveries, these early galaxies seem to be producing ionizing radiation at rates that defy earlier models. They're like cosmic overachievers, punching far above their weight in the re-ionization story. This has led scientists to rethink just how much credit galaxies deserve in clearing the cosmic fog. So while quasars were the flashy giants, galaxies were the unsung heroes, steady, relentless, and everywhere. Together, they turned the universe from a shadowy realm into the transparent cosmos we know today, setting the stage for everything that followed. Next, we'll pull back the curtain on the physics behind this grand transformation and why it didn't happen overnight. Now, let's peel back the layers of the science itself. How exactly did light tear apart the cosmic fog? Think of it like a cosmic game of tug-of-war between light and matter. At the heart of re-ionization are photons, those tiny packets of energy racing through space. When a high-energy ultraviolet photon slams into a neutral hydrogen atom, it's like a wrecking ball hitting a fragile structure. The photon's energy is so intense, it knocks the atom's lone electron clean off, leaving behind a positively charged proton. That's ionization in action, transforming neutral hydrogen, a shy electron clinging to its proton, into a free-roaming electron and a solitary proton. But why was this process so slow? Imagine trying to defrost a giant glacier with a hairdryer. Even if the hairdryer is powerful, melting the ice takes time because heat spreads unevenly. Similarly, the early universe was packed with hydrogen atoms, and ionizing them all required an overwhelming flood of UV photons. Stars and quasars didn't just flick a switch, they had to chip away at the cosmic ice, one region at a time. This explains why re-ionization wasn't a single event, but a drawn-out epoch lasting hundreds of millions of years. Here's where the cosmic sunrise analogy helps. Dawn on Earth doesn't happen instantly. Light creeps over the horizon, chasing away darkness bit by bit. In the universe, the first stars and galaxies were like the earliest rays of sunlight, creating small, glowing bubbles of ionized gas. Over time, these bubbles expanded and merged, just like how sunrise gradually floods the entire sky with light. But there's a twist: the universe's dawn wasn't uniform. Some patches cleared faster because galaxies clustered there, while other regions lagged behind, still shrouded in neutral hydrogen. What's truly mind-bending is the scale of this transformation. Every ionized hydrogen atom meant one more photon could travel freely without being absorbed. As more atoms were stripped of their electrons, the universe became less like a dense fog and more like a thin mist, eventually turning crystal clear. This transparency is why we can see galaxies billions of light years away today. Re-ionization literally cleared the cosmic air. So, was it just brute force from UV photons? Not entirely. The temperature of the gas played a role too. Ionized hydrogen is hotter, and hot gas resists clumping back together. Once a region was ionized, it stayed that way, creating a domino effect. This feedback loop helped re-ionization snowball, but it also meant the process had to fight against the universe's own expansion, which stretched and diluted the ionizing radiation. It's a cosmic balancing act we're still untangling. Next, we'll zoom out to the big picture. When exactly did this grand light show occur, and how do we piece together its timeline? The clues are hiding in the oldest light we can detect. Now, let's pinpoint when this cosmic transformation unfolded. The epoch of re-ionization didn't happen overnight. Current estimates place it roughly 1 billion years after the Big Bang, a blink of an eye in cosmic terms. To put that in perspective, our universe is around 13.8 billion years old today, meaning re-ionization occurred when the cosmos was less than 10% of its current age. That's like a child learning to walk before their first birthday, a rapid, pivotal moment in the grand timeline. But how do we know this? The evidence comes from redshift, a phenomenon where light stretches as it travels across the expanding universe. Think of it like the cosmic version of a siren's pitch dropping as an ambulance speeds away. The farther back we look, the more stretched or redshifted the light becomes. By analyzing the light from ancient quasars and galaxies, astronomers can spot the telltale signs of neutral hydrogen absorbing certain wavelengths. The point where these absorption features vanish tells us when the universe became mostly transparent. It's like finding a fossilized footprint in mud. The moment the mud dried, it stopped recording new steps. What's fascinating is how patchy the process was. Some regions of the universe cleared earlier than others, like uneven thawing in a spring meadow. Dense clusters of galaxies churning out UV radiation ionized their surroundings faster, while lonelier pockets lingered in darkness. This inconsistency is why pinning down an exact date is tricky. Re-ionization wasn't a single event but a gradual transition, like a dimmer switch being turned up slowly over hundreds of millions of years. To grasp just how ancient this era was, consider this. The light we're detecting from those early galaxies has been traveling for over 12 billion years to reach us. We're essentially peering back in time, witnessing the universe's awkward teenage phase full of energy, turbulence, and dramatic change. And yet, despite its youth, this period set the stage for everything that followed. Without re-ionization, the universe would still be a murky soup, hiding the glittering tapestry of galaxies we see today. Next, we'll uncover how an invisible cosmic architect, dark matter, helped orchestrate this grand transformation. Its gravitational pull shaped the very structures that made re-ionization possible. Now, shifting our focus to the unseen force that shaped the cosmic stage, dark matter. While it remains invisible to telescopes, its gravitational influence is undeniable. Picture dark matter as the invisible scaffolding of the universe, a vast network of gravitational pull that guided ordinary matter into the structures we see today. Without it, the gas that formed the first stars and galaxies would have been scattered too thinly, like flour dusted across a table instead of clumped into dough. Dark matter's role in re-ionization was indirect but critical. Its gravity created dense regions where hydrogen gas could accumulate, forming the seeds of galaxies. Think of it like a cosmic funnel. Dark matter drew in the raw materials, and ordinary matter followed, collapsing into stars and quasars that then flooded the universe with ionizing radiation. Simulations reveal this process vividly, showing how dark matter's tendrils formed a web-like structure, with galaxies blooming at the intersections like dew on a spider's silk. One of the most compelling pieces of evidence comes from computer models. When scientists simulate the early universe with and without dark matter, the difference is staggering. Without it, galaxies form late and sparsely, far too slowly to explain the rapid re-ionization we observe. But with dark matter, the simulations match our observations almost perfectly, showing galaxies igniting in dense clusters, their radiation bubbles overlapping like ripples in a pond. This scaffolding effect didn't just speed up re-ionization, it made it possible in the first place. Yet dark matter's influence didn't stop there. It also dictated the uneven pace of re-ionization we discussed earlier. Regions richer in dark matter attracted more gas, forming brighter galaxies that ionized their surroundings faster. Meanwhile, less dense areas lagged behind, creating that patchwork of light and shadow. It's why the universe didn't clear uniformly, but rather in waves, like sunlight breaking through a forest canopy in scattered patches. What's remarkable is how this invisible architect's blueprint still shapes the cosmos today. The same dark matter filaments that guided the first galaxies now underpin the vast superclusters we observe, proving that its role wasn't just a one-time act. It set the rules for how the universe grows, and we're seeing the echoes of that influence billions of years later. Up next, we'll zoom in on the battlefield where re-ionization played out the intergalactic medium, a sea of gas that transformed from a dense fog into a crystal-clear void. Now, let's step onto the battlefield where re-ionization's epic struggle unfolded the intergalactic medium. Imagine this as the universe's backstage, a vast sea of hydrogen gas stretching between galaxies, silent and invisible to the naked eye. Before the first stars ignited, this gas was neutral, like a thick cosmic fog that trapped light, leaving the universe in darkness. But as those early stars and quasars fired up, their radiation began to eat away at this fog, stripping electrons from hydrogen atoms in a process that would eventually clear the skies for good. Think of it like a massive curtain lifting. At first, only small holes appeared, bubbles of ionized gas around the brightest galaxies and quasars. But over hundreds of millions of years, these bubbles grew, merging like soap suds in a sink until they filled the entire cosmos. The change wasn't instant. It was a slow, uneven fight, with some regions clearing faster than others. Dense pockets of gas held out longer, like stubborn patches of morning mist that linger in valleys while the hills above bask in sunlight. What's fascinating is how this process left its fingerprints. The intergalactic medium didn't just vanish, it transformed. Astronomers can still detect its ghostly traces today, using quasars as cosmic flashlights. When light from a distant quasar passes through this gas, it creates an absorption spectrum, a barcode of missing wavelengths that tells us how much hydrogen was ionized along the way. It's like shining a light through stained glass and seeing which colors get absorbed, except here, the glass is the remnants of that ancient fog, and the colors reveal the universe's deepest history. This transition wasn't just about visibility. The ionization of the intergalactic medium fundamentally changed how the universe evolved. Once the gas was ionized, it became hotter and more diffuse, making it harder for new galaxies to pull in fuel. This put a brake on star formation in smaller galaxies, effectively shaping the hierarchy of the cosmos we see today. It's a reminder that re-ionization wasn't just a light switch, it was a thermostat regulating how and where galaxies could grow. And here's a twist: the intergalactic medium wasn't a passive victim. Its own structure influenced how re-ionization spread. Denser regions acted like speed bumps, slowing the advance of ionizing radiation, while thinner areas cleared almost overnight. This patchwork effect explains why some corners of the universe became transparent while others lingered in shadow, a cosmic game of hide and seek that played out over eons. To truly grasp the scale of this transformation, picture standing on a mountain at dawn. At first, you see only darkness, then, one by one, valleys below you fill with light as the sun climbs higher. That's what re-ionization looked like, a slow, glorious unveiling with the universe itself as the canvas. Coming up, we'll tackle one of the biggest challenges astronomers face, piecing together this ancient puzzle with technology that's straining to see back in time. How do you study an event that left no direct witnesses? The answer lies in the faint whispers of light from the edge of time itself. Now, let's confront the hurdles standing between us and the answers to these cosmic mysteries. Studying re-ionization isn't like examining a nearby galaxy or a bright supernova. It's more like trying to read a faded manuscript from billions of years ago, where every word is whispered and half the pages are missing. The challenges astronomers face are as vast as the era they're investigating. First, there's the problem of distance, and not just any distance, but the kind that stretches the limits of what light can endure. The light from the earliest galaxies and quasars has traveled for over 13 billion years to reach us. By the time it arrives, it's been stretched into the infrared part of the spectrum by the expansion of the universe, a phenomenon known as redshift. Our eyes can't see infrared light, and until recently, neither could most of our telescopes. Earth's atmosphere also blocks much of this light, making ground-based observations nearly impossible. It's like trying to hear someone's voice through a hurricane. The signal is there, but it's drowned out by noise. Then there's the issue of faintness. The galaxies that drove re-ionization weren't the colossal, bright structures we see today. They were small, dim, and often shrouded in dust. Detecting them is like spotting a single candle flickering on the other side of a continent. Even when we do catch glimpses, their light is often mixed with signals from closer, brighter objects, forcing astronomers to sift through cosmic static for the faintest clues. But perhaps the most frustrating challenge is time itself. Re-ionization didn't happen everywhere at once. Some regions of the universe cleared early while others lagged behind. To piece together the full story, we need observations spanning hundreds of millions of years, a snapshot of an era that unfolded in slow motion. Without a time machine, astronomers must rely on scattered remnants, like a detective reconstructing a crime scene from a handful of scattered breadcrumbs. Enter the James Webb Space Telescope, or JWST, a game-changer in this cosmic detective story. Launched in late 2021, JWST was designed specifically to tackle these obstacles. Its massive, gold-coated mirror captures 6 times more light than the Hubble Space Telescope, and its suite of infrared instruments pierces through cosmic dust and redshift with unprecedented clarity. Already, JWST has spotted galaxies from the dawn of the universe that are brighter and more numerous than theorists predicted, forcing us to rethink how quickly re-ionization might have occurred. But JWST isn't working alone. Radio telescopes like the upcoming Square Kilometre Array will map the distribution of neutral hydrogen during the cosmic dark ages, offering another perspective on how re-ionization unfolded. Together, these tools aren't just filling in gaps, they're rewriting entire chapters of cosmic history. The road ahead is still steep, but every flicker of light JWST captures brings us closer to understanding how the universe emerged from darkness. Next, we'll explore how supercomputer simulations are helping us test these new discoveries and why some models might need a cosmic overhaul. Now, let's step into the fascinating clash between theory and reality. Supercomputer simulations have long been our cosmic crystal balls, offering predictions about how re-ionization unfolded. These digital universes, built from equations and assumptions, paint a vivid picture of the early cosmos, dark matter scaffolding, gas collapsing into stars, and ultraviolet light carving bubbles of ionized hydrogen. But how do these simulations hold up when faced with actual observations? The answer is revealing and sometimes surprising. Take the timeline of re-ionization, for example. For years, simulations suggested it was a slow, gradual process spanning hundreds of millions of years. Yet, the James Webb Space Telescope has spotted galaxies so bright and so early that they hint at a universe lighting up faster than anyone expected. It's like thinking a campfire takes hours to build, only to discover someone had a flamethrower. These discrepancies aren't failures, they're clues. They force scientists to revisit their assumptions, tweaking variables like star formation rates or the escape of ionizing radiation from early galaxies. Then there's the matter of scale. Simulations often struggle to balance detail with breadth. Some focus on small patches of the universe, modeling individual galaxies with exquisite precision. Others zoom out to capture the entire cosmos but lose fine-grained details in the process. Imagine trying to predict a thunderstorm by studying a single raindrop, or the whole planet without noticing clouds. Real observations, like those from JWST, bridge this gap, showing us where simulations oversimplify or miss crucial physics. One striking example is the distribution of ionized bubbles. Simulations predicted these bubbles would grow unevenly, leaving patchy regions of neutral hydrogen. But JWST deep field images reveal a more complex tapestry, with some areas ionizing earlier and more uniformly than models suggested. This mismatch points to hidden factors, perhaps stronger radiation from quasars or unexpected interactions between galaxies. Every unexpected data point is a breadcrumb leading to a deeper understanding. The beauty of this back and forth is how it refines our knowledge. Discrepancies between simulations and observations don't mean one is wrong, they mean both are evolving. Each JWST discovery sharpens the simulations, and each refined simulation guides future observations. It's a cosmic feedback loop, with scientists constantly adjusting their digital universes to mirror the real one more closely. Looking ahead, the synergy between supercomputers and telescopes promises even greater revelations. Next-generation simulations will incorporate JWST findings, while upcoming missions like the Nancy Grace Roman Space Telescope will test these updated models. Together, they're not just reconstructing the past, they're rewriting the rules of cosmic evolution. And with every iteration, we get closer to answering the ultimate question: how did light conquer the darkness? Now, let's turn our attention to the grand finale of this cosmic transformation, the moment when the universe finally emerged from its dark cocoon. The end of re-ionization wasn't a sudden flip of a switch but a tipping point, a culmination of countless stars, galaxies, and quasars working in concert. Picture a foggy morning where the sun slowly burns away the mist, patch by patch, until the sky is clear. That's what happened to the cosmos, but on a scale so vast it's almost unimaginable. As more and more hydrogen atoms lost their electrons, the universe reached a critical threshold where the majority of this gas became ionized. This wasn't uniform. Some regions cleared earlier, others lagged behind like uneven melting ice. But eventually, the ionized bubbles overlapped and merged, creating highways for light to travel unimpeded. This marked the end of the so-called epoch of re-ionization, a defined chapter in cosmic history when the universe transitioned from opaque to transparent. It's a period astronomers pinpoint to roughly 1 billion years after the Big Bang, though the exact timing is still being refined with new data. What's fascinating is how this shift didn't just change the universe's appearance, it altered its very nature. Before re-ionization, light was constantly absorbed and re-emitted, trapped in a cosmic game of ping-pong. Afterward, photons could race across space for billions of years, carrying information about distant galaxies directly to our telescopes. This transparency is why we can peer so deep into the past today. Without it, the universe would still be a murky enigma, its early history hidden behind a veil of neutral hydrogen. The epoch's end also had a profound knock-on effect. With light now free to travel, the first galaxies could regulate their growth more efficiently. radiation pressure from young stars pushed away nearby gas, slowing star formation and preventing these galaxies from becoming overly massive too soon. This balancing act shaped the evolution of galaxies, influencing everything from their sizes to their chemical compositions. In many ways, the end of re-ionization set the stage for the universe we recognize today, a tapestry of galaxies, stars, and planets all bathed in starlight. Yet, even as we celebrate this milestone, mysteries remain. Why did some regions ionize faster than others? Were there late bloomers where neutral hydrogen lingered longer? These questions keep astronomers busy, with tools like the James Webb Space Telescope probing the faintest, most distant galaxies for answers. Each discovery adds another piece to the puzzle, helping us understand not just how the universe lit up, but how it grew into the vibrant cosmic web we call home. As we close this chapter, remember that the end of re-ionization wasn't an ending at all, it was a beginning. The universe, now transparent and buzzing with light, was ready for its next act, the age of galaxies, the birth of stars like our Sun, and eventually the rise of life itself. And it all started with those first, daring photons carving paths through the darkness. Now, let's step back and appreciate the full weight of what re-ionization left behind, a universe transformed. Imagine if the cosmos had remained shrouded in that primordial fog. The night sky would be blank, our telescopes blind, and the story of galaxies billions of light years away forever hidden. But thanks to re-ionization, the universe didn't just brighten, it opened up. This transparency wasn't just a cosmetic change, it was the foundation for everything that followed. With light now free to travel, galaxies could communicate across vast distances. Photons carrying ultraviolet radiation from young stars could escape their home galaxies, influencing the gas in intergalactic space. This created a feedback loop. The more stars formed, the more radiation escaped, further ionizing nearby hydrogen and preventing it from collapsing back into new stars too quickly. It's why the universe didn't burn through all its fuel in a frenzied burst of early star formation. Instead, it paced itself, allowing galaxies like our Milky Way to form gradually over billions of years. Consider the chemistry of life itself. Those early photons didn't just clear the cosmic fog, they forged the raw materials for planets and people. Heavy elements like carbon and oxygen, cooked in the cores of stars and scattered by supernova, could now mix freely through transparent space. Over time, these elements enriched galaxies, providing the building blocks for rocky planets, oceans, and organic molecules. In a very real sense, the air you're breathing right now was made possible by re-ionization. Without it, those heavy elements might have remained trapped in isolated pockets, and Earth, along with every living thing on it, might never have existed. Even the cosmic microwave background, the afterglow of the Big Bang, carries fingerprints of this epoch. The slight variations in its temperature tell us how matter clumped together during re-ionization, seeding the structures we see today. It's like finding fossilized ripples from the universe's first light show. And thanks to that transparency, we can trace those ripples all the way back, connecting the dots between the infant cosmos and the sprawling web of galaxies we observe now. But perhaps the most profound legacy is time itself. Because light could travel unimpeded, we're able to look back literally into the past. Every photon from a distant quasar or galaxy is a message from an earlier era, a snapshot of the universe growing up. This transparency turned the cosmos into a time machine, letting us witness its evolution firsthand. Without re-ionization, astronomy as we know it would be impossible. We'd be cosmic shut-ins, unaware of the universe's grand narrative beyond our immediate neighborhood. So the next time you gaze up at the stars, remember, you're seeing them because the universe fought its way out of darkness. That hard-won transparency didn't just shape the cosmos, it shaped our ability to understand it. And in doing so, it turned the universe from a silent, shadowy void into a place brimming with light, stories, and the potential for life. But even as we unravel the story of re-ionization, the cosmos keeps some of its secrets stubbornly hidden. Picture this like a detective halfway through a case. Some clues fit neatly, while others leave us scratching our heads. One of the biggest puzzles: why did re-ionization drag on for hundreds of millions of years? Think about it. The first stars and quasars appeared relatively quickly, cosmically speaking. So why didn't their light immediately flood the universe? One theory suggests that early galaxies were incredibly inefficient at leaking radiation. Thick cocoons of gas might have trapped most of their UV light, letting only a trickle escape to ionize the surrounding hydrogen. Another idea points to vast, dark zones, regions where few stars or galaxies formed, leaving patches of neutral hydrogen untouched for eons. These cosmic shadows could have slowed the process, like trying to defog a room one corner at a time. And speaking of patchiness, astronomers are still debating whether re-ionization happened uniformly or in a scattered, piecemeal fashion. Imagine bubbles of ionized gas popping up around early galaxies, slowly expanding until they overlap. Some simulations show these bubbles forming at different rates, creating a cosmic checkerboard of light and darkness, but proving that's tough. The signals from that era are faint, stretched by time into infrared whispers. Even our best telescopes struggle to map this ancient transition in detail. This is where future missions like the Roman Space Telescope come in. Set to launch in the next few years, it's designed to hunt for the faintest glimmers of early galaxies, potentially spotting those elusive bubbles of re-ionization. Its wide-field surveys could reveal whether the process was smooth or clumpy, like peeling back layers of cosmic history. Meanwhile, radio telescopes like the Square Kilometre Array aim to detect the faint hum of neutral hydrogen from the Dark Ages, offering another lens into this era. Then there's the mystery of missing actors. Some models predict that early galaxies alone couldn't have pumped out enough UV radiation to finish the job. Could decaying dark matter have lent a hand, or perhaps undiscovered populations of tiny, faint galaxies? The answers might rewrite textbooks. What's thrilling is that we're on the brink of breakthroughs. Every new telescope peels back another layer, offering fresh clues. Maybe soon we'll know why the universe took its sweet time waking up, and whether that delay was a cosmic accident or part of a deeper plan. Until then, the mystery fuels our curiosity, reminding us that the universe's greatest stories are still being decoded. Now let's turn our gaze to the most powerful time machine we've ever built, the James Webb Space Telescope. This marvel of engineering isn't just rewriting the rules of cosmic detective work. It's tearing up the old playbook entirely. Take those early galaxies, for instance. Before Webb, we assumed the universe's first galaxies would be small, faint, and struggling to shine through the primordial fog. But Webb's infrared eyes revealed something shocking: galaxies glowing with startling brightness, appearing barely a few 100 million years after the Big Bang. These cosmic overachievers are pumping out stars at rates that defy expectations, like toddlers bench-pressing weights meant for adults. Their sheer luminosity suggests they might have been key players in re-ionization, flooding the universe with ultraviolet radiation far earlier than we thought possible. One standout, the galaxy dubbed Glass Z13, spotted a mere 300 million years after the universe began. Its existence alone forces us to rethink how quickly structures could assemble in the infant cosmos. And it's not alone. Webb's deep field images, those glittering tapestries of ancient light, are littered with similar anomalies. Each one whispers the same tantalizing question: did re-ionization kick off sooner, faster, or in a more dramatic fashion than our models predicted? Then there's the puzzle of their composition. Spectroscopy from Webb reveals that some of these early galaxies already bear heavy elements: carbon, oxygen, even neon elements forged in stellar furnaces and scattered by supernova. That means stars were living, dying, and enriching their surroundings at breakneck speeds. This chemical maturity in galaxies so young hints at a cosmos that got its act together with breathtaking haste, like a fledgling orchestra mastering symphonies overnight. But here's where it gets thorny. If galaxies were this bright and abundant so early, why didn't they re-ionize the universe in a blistering flash? Some theorists suggest their light might have been trapped by dense gas halos, only leaking out slowly. Others propose that Webb is seeing an elite subset, the cosmic 1%ers, while countless dimmer galaxies remain hidden, their collective glow still too faint to detect. Yet every confounding discovery fuels progress. Webb's data is like a Rosetta Stone for re-ionization, helping us decode which galactic traits, size, star formation rates, gas content were the real drivers of this epoch. With each new observation, we're stitching together a richer, messier, and far more thrilling story of how light conquered the cosmos. And the best part, we've only just begun to scratch the surface. Now let's dive into one of astronomy's greatest quests, the hunt for the very first stars. These cosmic pioneers, known as Population 3 stars, are the universe's original firestarters, born from nothing but pristine hydrogen and helium. Finding them would be like uncovering the first brushstrokes on the canvas of creation. The challenge: these stars lived fast and died young. Theory suggests they were behemoths, up to several hundred times the mass of our Sun, burning fiercely for just a few million years before exploding in spectacular supernova. Unlike modern stars, they left no direct descendants. To spot them, astronomers must look for their ghostly fingerprints etched into the light of the early cosmos. One telltale sign would be their unique chemical signature. Population 3 stars contained no heavy elements, just hydrogen and helium, the raw ingredients of the Big Bang. If we could catch a whiff of their light with instruments like Webb's near-infrared spectrograph, we'd see a spectrum devoid of the metal lines that litter starlight today. It would be the purest light in the universe, a relic from a time before pollution by heavier elements. But there's a twist: these stars might not be entirely invisible. Some models suggest their supernova could have left behind ultra-bright afterglows called pair instability supernova, explosions so violent they briefly outshine entire galaxies. Telescopes like Webb are scanning the distant universe for these fleeting flashes, hoping to catch one in the act. Another clue lies in the ancient gas clouds they polluted. When Population 3 stars exploded, they seeded the cosmos with their first heavy elements. Finding pockets of nearly pure hydrogen today, like cosmic time capsules, could point back to their origins. The stakes couldn't be higher. Discovering a Population 3 star would confirm our theories about the universe's first light sources and shed light on how re-ionization began. Were these stars the primary actors in lifting the cosmic fog, or did galaxies steal the show? Their sheer size means they could have pumped out ultraviolet radiation at rates dwarfing modern stars, making them prime suspects in the re-ionization mystery. Yet for all their importance, the hunt remains a game of patience and precision. Webb's successors, like the upcoming 30-meter telescope, might finally have the resolution to spot these elusive giants. Until then, every anomalous flicker in the infrared sky keeps the dream alive. Finding them wouldn't just be a milestone, it'd be like meeting the universe's original architects face to face. Now let's take a step back and see how this ancient drama of re-ionization echoes into the far future of the cosmos. The universe we live in today, transparent, glowing with galaxies, and buzzing with activity, owes its very nature to that pivotal era when light first broke free. But this wasn't just a one-time event. The way re-ionization unfolded set in motion a chain reaction that continues to shape the destiny of everything we see. Think of re-ionization as the universe's first great awakening. By stripping electrons from hydrogen atoms, those early stars and quasars didn't just clear the cosmic fog, they fundamentally altered the universe's structure. Suddenly, light could travel unimpeded across vast distances, allowing galaxies to form and evolve without being smothered by dense gas. This transparency also meant that energy, whether from stars, supernova, or black holes, could spread farther and faster, heating the intergalactic medium and preventing it from collapsing back into darkness. But here's where things get even more fascinating. The way re-ionization played out directly influenced how galaxies themselves grew. Regions that ionized earlier became hotspots for star formation, while slower areas lagged behind, creating a patchwork of cosmic development. This uneven start helps explain why we see such variety in galaxies today, some teeming with stars, others quiet and diffuse. The conditions set during re-ionization essentially wrote the rulebook for how structure would emerge across billions of years. Fast forward to the present, and we're still feeling the repercussions. The universe continues to expand, and that expansion is accelerating, driven by a mysterious force we call dark energy. But without re-ionization, this expansion might have looked very different. A universe still shrouded in neutral hydrogen would have been denser, with gravity pulling matter together more strongly. By ionizing the gas, those early stars and quasars reduced its ability to clump, effectively giving dark energy a head start in shaping cosmic evolution. And what about the ultimate fate of the universe? Re-ionization's legacy points toward what astronomers call the heat death, a distant future where expansion has stretched space so thin that stars can no longer form and galaxies fade into darkness. By breaking the grip of neutral hydrogen early on, re-ionization ensured that the universe would evolve into the vast, diffuse expanse we see today, rather than a denser, slower-moving alternative. So when we look up at the night sky, we're not just seeing stars. We're witnessing the aftermath of a revolution that began over 13 billion years ago, a revolution that made our existence possible. The next time you gaze at a galaxy or a quasar's distant glow, remember, you're seeing the long-term effects of the universe's first great transformation. And that transformation is still writing the story of everything. Now, let's explore the intriguing alternatives that challenge our current understanding of re-ionization. While the dominant narrative points to stars and quasars as the primary actors, science thrives on questioning, and some researchers propose cosmic understudies might have shared the spotlight. One compelling theory suggests dark matter itself could have played a role. We know this mysterious substance outweighs normal matter 5 to 1, but what if certain types of dark matter particles decayed over time? If these hypothetical particles released energy as they broke down, that energy might have contributed to ionizing hydrogen. Imagine millions of invisible fireworks silently detonating across the early universe, their faint glow helping to lift the cosmic fog. While we've yet to detect such decaying dark matter, experiments like the James Webb Space Telescope could uncover clues in the temperature patterns of ancient gas clouds. Then there's the wild card of primordial black holes, hypothetical objects thought to have formed in the universe's chaotic first second. Unlike the supermassive black holes powering quasars, these would be tiny, some no heavier than an asteroid. But if they existed in vast numbers, their collective radiation might have supplemented re-ionization. Picture trillions of microscopic power plants humming away in the darkness, their emissions adding to the growing light. Recent studies of cosmic microwave background fluctuations are putting this idea to the test, searching for the unique fingerprint these objects would leave behind. Other scientists point to cosmic strings, theoretical defects in spacetime left over from the Big Bang. If these ultra-dense threads existed, their vibrations could have released bursts of energy capable of ionizing hydrogen. It's a radical idea, but that's exactly how science progresses, by daring to consider possibilities that initially sound like science fiction. What's fascinating isn't just these ideas themselves, but how they demonstrate science in action. Every alternative theory, no matter how unconventional, undergoes rigorous scrutiny. Observations from next-generation telescopes either support these hypotheses or force us to refine them. This back and forth is how we inch closer to truth, not by clinging to one explanation, but by testing every plausible pathway. As we gather more evidence from deep space observatories, we may find that re-ionization wasn't a solo performance, but an ensemble cast of cosmic phenomena. The answer likely lies in a combination of known and yet to be discovered processes, each contributing its unique verse to this grand cosmological symphony. Turning from the cutting edge of theory to the power of hands-on learning, let's explore how modern tools make this cosmic saga tangible. Understanding re-ionization requires stretching our imaginations across billions of years, but innovative educational resources act as time machines, collapsing eons into interactive experiences. Take Universe Sandbox, a physics-based space simulator where users can recreate the dawn of light firsthand. Imagine tweaking variables like the density of early hydrogen clouds or the birth rate of population 3 stars, then watching in real time as ionizing radiation spreads through your custom universe. The game's latest update even models the cosmic web of dark matter, showing how its invisible scaffolding guided the first galaxies into being. For visual learners, this turns abstract equations into a playable narrative, where you're not just hearing about re-ionization but actively shaping it. Planetariums worldwide have also joined the effort with shows like Cosmic Dawn, The First Light, using full dome projections to simulate the universe's transformation. The Hayden Planetarium's version employs spectral data from the James Webb Space Telescope to paint the sky with accurate hydrogen glow patterns, while narration explains how specific wavelengths correspond to ionization events. What makes these shows groundbreaking is their use of time compression, rendering hundreds of millions of years into a 10-minute sequence where audiences watch the cosmic fog dissolve before their eyes. For classrooms, the American Museum of Natural History offers a free Re-Ionization Lab module. Students analyze mock spectra from simulated early galaxies, distinguishing between neutral and ionized hydrogen signatures just like real astronomers. It demystifies tools like Lyman alpha line measurements by having learners spot these fingerprints themselves. Meanwhile, the Cosmic Re-Ionization Project's browser tool lets anyone explore 3D maps of the early universe, toggling between different theoretical models to see how they alter the ionization timeline. These tools share a common genius. They transform passive learning into active discovery. When you manipulate a slider to adjust quasar activity and witness how it accelerates re-ionization in a simulation, you're not just memorizing facts, you're internalizing the cause and effect relationships that shaped our universe. As we await future telescope data, these interactive experiences keep the wonder alive, proving that some of the most profound cosmic truths can indeed be held in the palm of your hand. But let's shift our gaze from the scientific tools to the cultural canvas, because re-ionization isn't just a chapter in astronomy textbooks. It's a wellspring of inspiration for storytellers, fueling some of the most imaginative narratives in science fiction. Take the cosmic struggle between light and darkness, a theme that echoes re-ionization's literal transformation of the universe. In Liu Cixin's The Three-Body Problem, the Trisolaran civilization lives in a chaotic 3-star system, where unpredictable cosmic eras alternating between extreme heat and cold force them to evolve in extraordinary ways. It's a haunting parallel to our own universe's early turbulence, where the first stars carved islands of light in an ocean of darkness. The novel even toys with the idea of a photoid, a weapon that manipulates cosmic-scale energy, mirroring the raw power of those primordial ionizing photons. Hollywood has tapped into this drama too. Films like Interstellar and Contact explore humanity's quest to decipher cosmic mysteries, much like astronomers piecing together re-ionization's puzzle. But lesser-known works dive deeper. The City at the End of Time by Greg Bear imagines beings surviving from the universe's infancy to its heat death, their biology shaped by the very radiation that re-ionized space. And in Light by M, John Harrison, rogue photons become sentient entities, a poetic nod to how light itself became the universe's dominant force after the Dark Ages. Even video games weave re-ionization into their lore. Destiny's Light and Darkness saga personifies these forces as cosmic deities, echoing how early stars and quasars battled neutral hydrogen across the cosmos. Meanwhile, No Man's Sky generates entire galaxies with procedurally generated stars, some coded to resemble population 3 stars, letting players stumble upon virtual relics of the re-ionization era. What makes these stories resonate is how they humanize the universe's grand narrative. When a Star Trek episode speculates about life existing in those first galaxies, or Doctor Who pits the Time Lords against creatures born from the early universe's shadows, they're asking the same questions scientists do: what thrived in that dawn of light? Could civilizations have risen and fallen before our own cosmic neighborhood even formed? This cultural cross-pollination goes both ways. Just as sci-fi borrows from astrophysics, terms like cosmic dawn and re-ionization frontier now pepper screenplays and novel drafts thanks to documentaries and telescope press releases. It's proof that the universe's greatest origin story isn't confined to labs. It's alive in our collective imagination, reshaping how we see our place in the cosmos. Now let's clear up some cosmic confusion. When we talk about re-ionization, it's easy for the imagination to run wild. Picture a sudden, violent explosion of light tearing through the darkness. But the truth, it was more like a slow, cosmic sunrise. Think of it as a fog lifting over billions of years, not a light switch flicking on. Those first stars and quasars didn't blast the universe into transparency overnight. They worked gradually, their radiation peeling back the veil of neutral hydrogen one region at a time. Another mix-up, the so-called cosmic dark ages. The name sounds like total blackness, but it's a bit misleading. Yes, the universe was filled with neutral hydrogen that blocked visible light, but other wavelengths, like radio waves, could still travel freely. Imagine trying to see through thick fog with regular sunglasses. Swap those for night vision goggles and suddenly you'd spot hints of structure. That's why astronomers used tools like radio telescopes to study this era. It wasn't a pitch-black void, just a universe playing hard to get. Then there's the myth that re-ionization was a one-time event. In reality, it was patchy and uneven. Some parts of the universe ionized earlier than others, like clouds breaking up at different times across the sky. Dense regions near early galaxies became transparent faster, while remote pockets of hydrogen held out longer. This messy, uneven process is why telescopes like the James Webb Space Telescope are so vital. They help us map these variations, revealing where and when light first broke through. And let's tackle a big one, the idea that re-ionization created light. Nope. Light existed during the Dark Ages, it just couldn't travel far without getting absorbed. Re-ionization didn't invent light, it gave it freedom. Picture a room full of people all talking at once. Until the crowd thins out, you can't hear individual voices. Re-ionization was the universe finally quieting down enough for light signal to come through clearly. Finally, don't confuse re-ionization with the Big Bang. They're separated by hundreds of millions of years. The Big Bang was the universe's fiery birth, while re-ionization was its awkward adolescence, a turbulent transition from murky chaos to structured clarity. Getting these milestones straight helps us appreciate just how patient cosmic evolution really is. So next time you hear cosmic dark ages or re-ionization, remember, the universe's story isn't built on dramatic explosions, but on slow, relentless change. And that's even more awe-inspiring. Now, let's shift gears to something truly exciting: how you can be part of this cosmic detective work. You might think unraveling the mysteries of re-ionization is reserved for astronomers with giant telescopes, but here's the twist. amateur stargazers and curious minds like you are already making real contributions. Take the Zooniverse platform, for example. This online hub lets anyone, yes, even without a science degree, help classify galaxies, spot distant quasars, or flag unusual cosmic structures in telescope images. Imagine scrolling through snapshots from the James Webb Space Telescope, tagging fuzzy blobs that could be some of the universe's first galaxies. Every click brings researchers closer to piecing together the re-ionization puzzle. And here's the kicker: volunteers have co-authored scientific papers based on these discoveries. That's right, your living room could become a frontier of astrophysics. But it's not just about galaxies. Projects like Radio Galaxy Zoo train you to map jets from supermassive black holes, key players in re-ionization. Others focus on spectral data, teaching you to read the fingerprints of light that reveal ionized gas. The best part, these tools often come with tutorials, so you're never thrown into the deep end. Even if you mix up a spiral galaxy with an elliptical one at first, the crowdsourced model ensures mistakes get caught, like a cosmic version of peer review. And if you're more hands-on, consider joining a local astronomy club. Many track variable stars or monitor active galactic nuclei, phenomena linked to the same energetic processes that drove re-ionization. With affordable gear, even a decent backyard telescope and a DSLR camera, you can contribute data to global databases. For instance, measuring the brightness of distant quasars over time helps professionals gauge how their radiation interacts with intergalactic hydrogen. Here's why this matters: re-ionization wasn't a solo act. It was a chorus of light from countless sources, and understanding it requires vast datasets. No research team, no matter how talented, can analyze millions of galaxy images alone. By pitching in, you're not just observing history, you're helping write it. So next time you gaze up at the night sky, remember, those ancient photons aren't just for scientists, they're for anyone willing to look, learn, and lend a hand. The universe's greatest story is still being told, and you've got a front row seat. Now, let's turn our gaze toward the horizon of discovery, because the story of re-ionization is far from finished. The next generation of telescopes promises to peel back even more layers of this cosmic mystery, and what they might reveal could rewrite our understanding of the universe's dawn. At the forefront is LUVOIR, the Large Ultraviolet Optical Infrared Surveyor, a proposed space telescope with a mirror so vast it could dwarf even the James Webb Space Telescope. Picture this, a colossal eye in the sky, designed to capture the faintest whispers of light from the very first stars and galaxies. LUVOIR ultraviolet vision is key because that's the wavelength where re-ionization's fingerprints are clearest. It could spot ionized hydrogen bubbles forming around early galaxies, tracing how they grew and merged to lift the cosmic fog. And with its staggering resolution, it might even catch population 3 stars in their death throes. Those elusive giants whose explosions seeded the universe with heavier elements. But LUVOIR isn't alone. Projects like the Habitable Worlds Observatory and the European Extremely Large Telescope are joining the hunt, each armed with specialized tools. Some will map the intergalactic medium in 3D, revealing how ionized gas webs connected the early cosmos. Others will analyze quasar light with precision so sharp, they'll detect variations in re-ionization's timeline, like finding patches of the universe that cleared earlier or later than others. Imagine uncovering a cosmic desert where re-ionization lagged, or a hotspot where it raced ahead. These anomalies could hint at unseen forces, from exotic dark matter interactions to primordial black holes. Then there's the tantalizing prospect of spotting dark stars. Theorized to be fueled by dark matter annihilation, these bizarre objects could have been bright enough to contribute to re-ionization, yet invisible to current telescopes. Next-gen instruments might finally catch their glow, adding a wild card to the re-ionization playbook. And let's not forget the role of artificial intelligence. As datasets swell to petabytes, machine learning will sift through the noise, identifying patterns human eyes might miss. AI could flag a weird spectral line in a distant galaxy as the signature of an entirely new light source, something we haven't even imagined yet. What ties all this together is a single, thrilling idea. We're on the verge of seeing deeper into the past than ever before. The next decade could deliver snapshots of the universe at just 200 million years old, a toddler by cosmic standards. With each observation, we're not just filling gaps in a timeline. We're piecing together how light sculpted the cosmos, and in turn, how that process made our existence possible. The tools are coming, the targets are clear, and the discoveries, they'll be nothing short of revolutionary. Now, let's take a step back and marvel at the bigger picture, because re-ionization isn't just a chapter in cosmic history. It's a profound reminder of our own origins, woven into the fabric of the universe. That ancient light born from the first stars and quasars didn't just illuminate empty space. It set the stage for everything that followed, including us. Think about it, every atom in your body, every breath of oxygen, every trace of iron in your blood was forged in the hearts of stars. But those stars couldn't have existed without the universe first becoming transparent. Re-ionization was the cosmic gatekeeper, the moment when light broke free and allowed matter to clump into galaxies, stars, and planets. In a very real sense, we owe our existence to that primordial dawn. This isn't just science, it's poetry written across billions of years. The same ultraviolet rays that stripped electrons from hydrogen atoms also carved the pathways for life to emerge. It's humbling to realize that the universe had to undergo this violent, radiant transformation just so we could one day look up and wonder about it. And yet, for all we've uncovered, there's still so much mystery. Why did re-ionization unfold the way it did? Were there moments of chaos, or was it a slow, inevitable unfurling? These questions tap into something deeper than astrophysics. They speak to humanity's eternal quest to understand where we come from. Every culture has its creation myths, but now we have something even more extraordinary, a scientific narrative that links us directly to the first light in the cosmos. So the next time you gaze at the night sky, remember, you're not just seeing stars. You're seeing the aftermath of a revolution, the legacy of an era when darkness gave way to light. Those photons have traveled across eons through expanding space and time just to reach your eyes, and in that connection there's a kind of magic. The universe, once opaque and unknowable, now reveals itself to us piece by luminous piece. This is the gift of re-ionization, not just a transparent universe, but a story written in starlight, waiting to be told. And as we keep searching, probing deeper into the past, we're not just uncovering facts. We're rediscovering our place in a cosmos that somehow, against all odds, made room for us to shine. So let's keep looking up, let's keep asking questions. Because every answer we find is another thread in the grand tapestry of existence, woven from the very light that made us possible. Now, as we bring this cosmic journey to a close, let's take one last look at the incredible story we've unraveled together. From the silent darkness of the early universe to the blazing dawn of the first stars, re-ionization was the transformative moment that lit up the cosmos. It wasn't just a flicker, it was a revolution, a cascade of light that tore through the fog of neutral hydrogen and sculpted the universe into the transparent, star-filled expanse we know today. Think of it like this: re-ionization was the universe's first act of self-expression. Before it, everything was hidden, a shadowy canvas. But once those first stars and quasars ignited, they didn't just shine, they rewrote the rules. They carved out the pathways for galaxies to form, for stars to birth planets, and for those planets to one day cradle life. It's a chain reaction that stretches from the primordial past to this very moment as you watch this video. And that's the real wonder here. We're not just observers of this story, we're part of it. But here's the thing: science never stops. Every discovery, like the jaw-dropping images from the James Webb Space Telescope, peels back another layer of this cosmic mystery. We're living in a golden age of astronomy, where tools like Webb and future observatories are giving us front-row seats to the universe's greatest show. Who knows what we'll find next? Maybe the first direct evidence of population 3 stars or a quasar are so ancient it redefines our timeline. The questions are endless, and that's what makes this so thrilling. So, if this journey through cosmic history has sparked your curiosity, don't let it end here. Hit that subscribe button to join us as we keep exploring the universe's biggest mysteries, from black holes to dark matter and beyond. Drop a comment below and tell us what part of re-ionization blew your mind the most. Was it the sheer scale of it, the way it connects to our very existence? We'd love to hear your thoughts, and remember, every time you look up at the night sky, you're seeing more than just stars. You're seeing the legacy of that first light, the echo of a transformation that made everything possible. The universe went dark so it could shine brighter, and now, billions of years later, we get to witness the result. So keep wondering, keep asking, and most of all, keep looking up. The cosmos still has so many stories to tell, and we can't wait to share them with you. Thanks for watching, and we'll see you in the next adventure.